Welcome once again in the class of design of steel structure. So we have already seen the design procedure and specification for the welded connection. So in this lecture we are going to see the problems on design of welded connection. I am Mr. S.S. Saugale, Assistant Professor Civil Engineering Department. So first problem we are taking, that is two plates of 16 and 14 mm are to be joined by butt weld as shown in figure. The joint is subjected to tensile force of 280 kN. Due to some reason, the effective length of weld could provide only 175 mm. Check safety of joint. So first case is a single V butt with incomplete penetration, and second is double V butt with incomplete penetration. So you might remember, in case of complete penetration, it shows the strength same as the member, but in case of incomplete penetration, in case of butt joint, we have to calculate the uh, by using the formula. So we are assuming the allowable stress in butt weld in tension is 150 newton per mm square. So first case, that is single V with incomplete penetration. So as per IS specifications, the throat thickness, we have the formula, that is 5 by 8 into T. 5 by 8 into T. So we have the plate here, we have the two plates. There is one is of 16 mm, one is of 14 mm. So we are taking the lesser plate over here. So 5 by 8 into 14, which becomes 8.75 mm, and we have the effective length as specified in the problem, that is 175 mm. So the strength of plate is 8.75, which is the throat thickness, into 175 into this strength of weld in tension that we have assumed. So that becomes 229.68 kilonewton, which is again lesser than this 280 kilonewton. So the connection is unsafe because we are designing it for the 280 kilonewton. So, and remember, we are checking the safety of the joint only. Hmm? So in case of single V incomplete penetration, it is unsafe. Now the double V with complete penetration. So basically, again I am moving to the just earlier part, that is this is the single V and this is the double V. We have seen this into in the earlier lectures. So the double V with incomplete penetration rather. So the throat thickness with complete penetration. So the throat thickness is thickness of the thinner plate, that is 14 mm. The strength of the weld 14 into 175 into the strength of the weld, and that becomes 367.5, which is greater than 280, which is safe. So actually this should not be there. This is complete penetration. Rather, in complete, we have the complete penetration over here. So remember that thing. Now, a tie member in a truss girder is 250 mm by 14 mm in size. It is welded to a gusset plate 10 mm thick by fillet weld. The overlap of the member is 300 mm. The size of the weld is 6 mm. Find the strength of joint if welding is done as shown in figure. So allowable shear stress here is 108 Newton per mm square. So in figure we can see the welding has been done in this way. It's like this. These are the end returns. Welding has been done in this way. So the effective length of the weld. So here it is 300 mm. So twice into 300, this 300 and this 300 and 250. That is here. So it becomes 850 mm. So the effective throat thickness is 0.7 into 6. Remember, this is the fillet weld, so K into S. So that becomes 4.2 mm. So the strength of fillet weld, that is length of the weld into the effective throat thickness into this shear strength. So that becomes 3850 uh, this 3,85,560 Newton, that becomes 385.56 kilonewton. So this is the strength of the particular joint. Now what we have the extension in that problem, what increase in strength if the weld is done all around? So remember, earlier it was like this, it is from the three sides, and now what we are doing, where is the cursor? Ah, what we are again increasing the weld length in this direction also. So the change yet that becomes, so we are having the 2 into 300 and 2 into 250, so that becomes 100 and 1100 or 1100 mm. So the strength becomes the length of the weld, the throat thickness, and this is the strength. So that becomes 498.96 kilonewton. So the strength increased by this 498.96 minus 385.56, that becomes 113.4 kilonewton. Now the next problem. A tie member consisting of angle ISA 80 by 50 by 8, that is Fy is given, that is 250 MPa, is welded to a 12 mm gusset plate. Design weld to transmit a load equal to the full strength of the member. So first we have to calculate the full strength of the member. Let P be the strength of the member. So this way, here you can see this particular member has been connected with the plate in weld has been provided in this and in here only. So these are the properties of the particular member which we have taken from the steel table. So here you can see from steel table the properties of steel section, that is area of the member, that is 978 mm, cx, that is distance from the this this is the cx, this is the cx. So you can see in the steel table, this is cxx, this distance, which gives the cg of that particular member in x direction. And we have sigma 80, that 0.6 fy, so that becomes 0.6 into 250, that is 150. So the load which member can carry is P equals to cross sectional area into permissible stress. So cross sectional area is 978 and the permissible stress is 150. So the member can carry the load 146.7 kilonewton. So weld will be designed to transmit a force equal to 146.7 kilonewton. So this way we have calculated the full strength of the member. So here it has been given over here. This is full strength of the member. So we have calculated the full strength of the member. Further, the force resisted by the lower side of the angle, that is P1. So P1 has been given over here. So 146.7, that is this, into 80, which is the length of this particular leg. This entire length is 80. So this is 80 by 50 by, so this 80 minus 27.3, that is cxxx divided by 80. So Amongst this 146.7, the P1, that is lower side of the angle, carrying the load this much, that is 96.638. So, and force resisted by the upper side, that is 146.7 into 27.3 divided by 80, that is 50.061 kilonewton. So here we have calculated the force resisted by both the sides, that is below part of the CG and above part of the CG. This is the CG which comes over here. Let me clear the screen. So this is the CG of this particular, that is in XX direction. We have this CXX distance, that is 27.3. Sorry for the it is scribbling in the side. So this is 27.3, and this entire length is, this leg is of 80 mm. This is of 80 mm. So this lower part can carry the load equals to this 146 minus 80 minus 27.3 divided by 80. This is the entire load, and part of this, that is 96.63, will carried by this lower section, that is this overhanging leg. This lower leg, and remaining part is carried by this particular upper portion. So let us assume the size of the weld, that is x equals to 6 mm, which should be greater than 3 mm. So the effective throat thickness, that is K into S, that is 0.7 into 6, which is again 4.2. So L1, that is the length of uh, the connected leg, and that this lower side, connected lower side leg. So that is 96.638 into 10 raised to 3 divided by 4.2 into 108, which is the strength of the weld. So that becomes 213.4. We are providing 215. And this L2, which is this force 50.061 into 10 raised to 3 divided by 4.2 into 108. So that becomes 110. We are having here 115 mm. So this way we can calculate the both weld lengths, that is L1 and L2. So L1 is 215 and L2 is 115. So L1 we are providing over here. This is the L1, which is for the higher force. Right, here is this. This is L1, and this becomes, either you can take it from this side or this side. So this is right. You can provide it at any side. So this is L1 and this is L2. Now next problem, that is design same problem with for welding done from all sides. So in last we have done welding from this L2 and L1. So now we are doing from all the sides. So the total length of the weld is L1 plus L2 and plus 80. So this 80 remains constant. This 80 remains constant. So the strength of the weld per mm, that is, we are having the throat thickness over here into strength, that is 108. So that becomes 453 Newton. Remember, this is strength of the weld per mm. So equating the strength of the total weld to the total force. So we are having the total length, that is L1 plus L2 plus 80 into length per mm equals to 146, which we have calculated earlier. So that becomes, we are getting L1 plus L2 equals to 243 mm from this equation. So taking moment at the top edge of the angle section. So we are taking moment over here. Where is the cursor? We are taking moment over this point. So now 453.6 into 80, which is the uh, force carried by this 80 mm side. This 80 mm side. 453, which is this, into 80 into 80 by 2. This is 80 by 2 because this force is at the center over here, plus 453.6 into L1 into 80. So the force carried by this, which is over here in this particular area. So L1 into that particular force. So 453 into L1 into 80 is this distance, that is the lever arm of this particular force. This is 80 equals to 146, which is the force coming through this particular member, which is somewhere over here in the CG of this member, and we know this CXX distance. So how much it is? CXX, this is quite we have to be getting used to of these things. So that is 80 minus 27.3. So we are taking moment over here. So this becomes, this distance is cx minus 20 80 minus cxx, that is 27.3. cxx is 27.3, we have seen earlier. So by solving this equation we will get the L1 equals to 173.4 mm, and we are providing it 175 mm. So again we have this thing, that is this total well length equals to L1 plus L2 equals to 80. So by using that equation we will get this L2 over here, this is L2 over here 70.37, we are providing it 75 mm. So this way we can calculate the, when the weld is provided from the three sides, or in earlier problem when the weld is provided only on two sides. So this is the welding for the angle section in the trusses. So the reference for the today's lectures are book of Design of Steel Structure by S.K. Duggal, Tata McGraw-Hill publication. Thank you.